So now we want to look at work for extension 2 on integration and learn a few techniques, but also just look at problems and try and be a bit more discerning on how we're going to solve some of these problems as opposed to what we did in extension 1. And hopefully be a bit more experienced, a bit more have these skills to recognise that we can do problems a little bit more quickly and don't have to go through a lot of the processes we did in extension 1. That's the aim. We'll see how we go. So what we want to look at first is the idea of reversing the chain rule. So the idea, well, when we did the chain rule for differentiation, can we reverse that to be able to solve and do integration problems? So for example, this one here, like 2x outside of x squared plus 1 all squared. Now, if we consider the derivative of x squared plus 1 all cubed, which, if we derive that, we're going to get to a x plus 1 all squared. So in integrating, we'd go back to that. So if I'm going to consider that derivative, I get 3 outside of x squared plus 1 all squared times 2x. So because I'm going to use the chain rule on that. So that which would give us 6x. So the 2x is there. All we've got is a 3 that shouldn't be there technically. When we're looking at our integration we need to solve. So I can change this to be 1/3 times 3 times the 2x outside of x squared plus 1 all squared, which allows me just to reverse that chain rule to get back to x squared plus 1 all cubed. Now, in the extension 1 course, we did that by substitution. There's no reason why you cannot use substitution to do a problem like this as well. The thing is, for these ones, you won't be given the substitution to be done. You'll just get that problem and asked to integrate that. Now, that doesn't mean you can't use substitution. You can't pick out, okay, if I let u be equal to x squared plus 1, and then get du as 2x dx, and then be able to solve and get down to the same answer, that you're going to be wrong. No. What we're hoping, though, is that you can start to recognize that idea that, well, if I'm going to integrate something like this, well, that's what I would get if I took the chain rule and applied it on the x squared plus 1 all cubed. If you start to recognize that, then that's excellent. That's starting to make life easier for yourself. Let's have a look at this one. 2x outside of 1 minus x squared all to the power of 4. So again, we can treat it in this way, like deriving 1 minus x squared gives us 2x. So it's only a positive 2x. So that's where we get the minus 2x out the front here. But because we can't change it, so we put a minus there. And the derivative of that was just the minus 2x, which is already there. Which if I put the minus out the front, I'm reversing the chain rule. So adding 1 to the power, dividing by the power as such, with a negative out the front. And that's when we get that reversal in that situation. We also consider the 1/5 and the minus 5. Well, we can do it that way as well to get our integration that we need to do there as well. But we consider that. This one, minus sine of x on cos squared of x. So again, if I consider that if the cos squared x is going to be, if I consider the derivative of cos x to the power of minus 1, and we can see that gives us sine of x over cos squared x. And we've got minus there. So again, just put the minus out the front. And we know now we know the integral of that one would back to inverse the cosine of x to the power of minus 1, or minus 1 on cos of x, so the minus 1 out the front. Again, you can see how I've done it with substitution. If you're happy with the substitution, then go for it. Then by all means, be able to do that substitution. X outside of the square root of 1 minus x squared, or 1 minus x squared to the power of a half. So again, if I'm going to integrate that, that's going to be something like 3 to the power x to the 1 minus x squared to the power of 3 on 2. So what would the derivative of that be? Well, that would come down to minus 3x 1 minus x squared to the power of a half when we do the chain rule. So if I've got to that point, I'm really close because I just need a minus 3x, which means I could put the minus 1/3 out the front, which means it's going to go back to what we've got when we derived it there. So that's where that one starts to come from. Again, there's the situation if we do the substitution. And again, if you have a look there and happy with that. So x squared minus 1 to the power of a half, I consider that differentiation. That would give me the x to the power of minus a half there, to bring the half down, to multiply by 2x, and gives me x on the square root of x squared minus 1, which happens to be exactly, I don't have to do anything there, that happens exactly to be the reversal of the chain rule there. So again, considering that this might, because I've got the x out the front, and the derivative of that would be involving the x, then I have to, that's where it starts to tell me I could be having a situation where it's reversal of the chain rule, and I can consider it. Now, these ones here are situations where you will have to do a substitution. But in the extension 2, unlike the extension 1 where we get given the substitution all the time, you might be given a substitution, you might not. You might have to be able to look at the situation and go, okay, is it a reversal of the chain rule, which technically this is, but you might have to choose a substitution. So we're looking at this situation here. If we let u be equal to secant of x, then we know the derivative of that is sec x tan x. So secant of x to the power of 5 times tan x could be written this way. So we decompose it to get secant x to the power of 4. Sec x tan x could be written as u to the power of 4 du, or that's u to the power of 5 on 5, which gives us 1 on 5 secant x to the power of 5. Now that's again, you don't have to do the substitution. You could see it as a reversal of the chain rule as well, because derivative of sec x is sec x tan x. So we can, if we recognise the function times the derivative of the function of the power times the derivative of the function, and we can just reverse it and get to there. If you were happy to go straight from there to there, then that would be okay. That would be okay. Again, same thing here. You could do a substitution, like I've done here. Again, you could see that it's a reversal of the chain rule, because the derivative of cos x to a power, derivative is sine x. So it's minus sine of x. So you can rearrange it and put a minus out the front, and then reverse your chain rule. Or you could do the substitution as we've done there. Not a problem to do that. Sine x all cubed times cos of x. Again, you can do the substitution like we've done here, or just reverse your chain rule if you're confident enough to do that. And that would give you sine x to the power of 4 over 4 when you do your substitution. Again, tan x to the power of 4, sec squared x, reminding yourselves that sec squared x is the derivative of tan x. And we've put it into the substitution and do that. Or, again, if you realise the reversal of the chain rule, you're quite happy to be able to do that. The derivative of tan x power of 5 would be the 5 times tan x to the power of 4 sec squared x. So 9 here, this one's a little bit harder. Bit hard to try and recognise this as a reversal of a chain rule as such, but again, it's what it is. So the derivative of either the inverse sine of x would be either the inverse sine of x times 1 on square root of 1 minus x squared, which is the derivative of the inverse sine of x. But again, can we make these connections? As an extension 2 student, we're hopefully starting to see these connections being made more often with these types of problems. So we recognise it's the derivative of function times the derivative, which the reversal of the chain rule just gives it back to either the inverse sine of x. Again, you could do the substitution. Let it e to the power of u, where u is the inverse sine of x, gives you that du as 1 on the square root of 1 minus x squared dx, which happens to be in the problem. Either u du, well, it starts to be able to integrate that pretty easily. So there's some examples of reversing the chain rule. Again, you won't see substitutions for those. You'll just see the problem straight out. if you are happy to go and use a substitution in it, that's fine. That's nothing stopping you from being able to solve these problems in any way, shape, or form you like. The more you're able to recognise a reversal of the chain rule, the better you're going to be, though, in a lot of situations. But again, experience is going to tell you that. So you'll be able to, the more you do, the better you get, as we say quite often in this respect, that you're going to see them. And the more you can see them, the more you'll be able to recognise that reversal.